activity or any discussions we make in class you should consider. You may find it in the exam. Okay, fine. So what is the final relation يا شباب you got? If we replace the thyristor with diode, what is the final relation you got? Can anybody say the relation to me?
Square root of 2 VRMS.
So معلش the bin يعني start making some problems again. So VT equals square root of 2
VRMS over by multiplied by cosine alpha plus 1.
Exactly. Very good. This is the right relation. So if we replace the thyristors with diode, this will be the relation now. If you now apply the firing angle at any instant and compare the average value between this relation and that relation, you will find the average value here is higher. This is the concept now. Why? Because you already removed the negative part from this relation. And if you remove the negative part, for sure the average value will be high. So this is the benefits of using freewheeling diode. This is the advantage of using freewheeling diode. Okay, fine. Also, the discussion is very important. The concept, you should understand the concept because you may be asked in MCQ to drive the equation or to write the right relation or like that. Okay, so you have to be ready for any questions like that. طيب. تفضل يا شباب، تفضل.
Does this circuit when we add diode act like a half wave rectifier?
No, it's still full wave. Half wave rectifier is just one thyristor. This is the half wave, which means it can only act with one half cycle, positive or negative. This is the meaning of half wave. But here, because you already make differences or controls both of half cycles, this is called full wave. But the circuit is called full wave semi-controlled. Why semi-controlled? Because you have half of the elements controlled element and the other half is uncontrolled. So it's called semi-controlled. We solved one example regarding the half wave, شباب. The half wave, the single phase rectifier, and the other solved example here for a three phase rectifier. So let's continue solving our problems. So we have here speed of 125 horsepower, 600 volt, 1800 RPM, separately excited DC motor is controlled by a three phase full wave converter. So this circuit, this problem will operate the motor using three phase rectifier, not single phase. So you have to recognize the relation. The converter is operated from three phase 480. What is the 480 now, Shabab? Is it phase or line, RMS or maximum? What is this value now?
Three phase RMS.
It's three phase, we know, but RMS RMS phase or line?
Line.
So this is line value. So if you need the phase value, which is already derived in the relation, you should divide by square root of 3. Okay, 60 hertz supply. This is all for the AC supply of the rectifier. Now, the rated armature current of the motor is 165 amps, and the motor parameters are given. You have the resistance, you have inductance, and the flux constant or the motor constant. The converter and the AC supply are considered to be ideal. Find no load speeds at firing angle of alpha equals 0 and alpha equals 30 degrees, and assume that at no load the armature current is 10% of the rated. So we have the rated, so the armature current at no load is only 16.5 amps, and also it's continuous. Okay, Shabab. So for now, Shabab, how we can get the no load speed? Shabab, you know the relation of the no load speed. What is the relation of no load speed? If we consider the current as 10%, So the relation can be obtained from, what is the relation? Who can شباب يعني join us? Relation of no load speed.
Omega no load equal
Omega
V
no
terminal
load equals
V
V
terminal.
terminal over K phi. Is it right? But
Yes.
this is approximated solution. Because we said here V terminal, you know the right solution, omega equals E A at no load over K phi. But we assume that V terminal equals EA at no load. However, here it's stated that the no load current is given. So you shouldn't neglect that. So we should say now it's equal to V terminal minus IA no load multiplied by RA over value of KA phi. You got it, شباب? يعني here we have already the value of no load current, so you should not neglect that. Okay? Don't use the value of V terminal over K phi directly. So for here, شباب, we can substitute in the relation. You know the value of no load current, and you know the value of V terminal. Okay? According to the firing angle used, you will get it at alpha equals 0 and 30. So you can obtain the value of omega at different voltage values given. This is the way. So for now, let's now give the relation of the converter. We can say now VT, which is the average value of the rectifier, equals 3 multiplied by square root of 6 multiplied by V phase, which is nothing but V line over square root of 3, divided by the value of pi, 3.14, multiplied by cosine alpha. So the relation now is 648 cosine alpha. This represents the average value of the output voltage of the rectifier. Now, you need to obtain the value of speed. Assume at each case, firstly, at alpha equals 0. So we can say now at alpha equals 0, so cosine 0 equals 1. So the value of V terminal will be 648. Now substitute in the equation, obtain the value of EMF, and then obtain the value of speed. Okay, شباب? This is for alpha equals 0. Similarly, we can repeat at alpha equal 30. As you can see, at alpha equal 30, the output voltage is lower than the voltage at alpha equals 0. At alpha equals 0, the voltage was 648. As you can see here, the voltage is reduced. It's 561 volt. So we can obtain again the value of EA at this firing angle and obtain the required voltage, the EMF voltage, and then substitute in the relation to obtain the value of speed. As you can see, speed here is is lower than the previous speed. Why? Because the voltage at firing angle equal 30 is lower than the voltage at firing angle equal 0. Right. Is there any question, شباب? Is it clear now? How we can control the motor speed by means of controlling firing angle?
Yes.
So شباب, we can say now at firing angle equals 0, we can get the maximum possible speed. This is the highest value of speed control range. And at lower value of firing angle, at lower value of voltage, we can obtain the lower value of speed. But what will be the value? It depends on the operation of your converter. So here, for instance, number B, it's required to find the firing angle to obtain the rated speed at 1800. So we have here a definite speed, and we need to obtain the value of firing angle. So, and it's opposite to what we have made in part A. Now you have the speed and you need to obtain the firing angle. طبعا simply يا شباب, we can start calculating the EMF. So EA equals KA phi multiplied by our speed. Take care يا شباب, here the value of motor constant is given as a function of RPM, not radian per second. For that, we here multiplied directly by the speed in RPM. So this is now the EMF. Simply substitute in the equation at rated current as it is discussed at full load condition. So we can say V terminal equals E plus IA rated multiplied by RA. So this is now the voltage at the motor terminal. Simply you have the voltage at the motor terminal, which is representing the average value of the output rectifier voltage. We can now say V, which is V max, which was 648 cosine alpha. This is the average voltage relation of the converter here. It's equals to 608, which is the output average voltage at our operating condition at speed of 1800. So now you have a relation as a function of alpha. You can get easily the value of alpha. طبعا يا شباب يعني you have to check your solution. Now the value of alpha is 20 degrees. You can compare now between the voltage at 20 and 0 or 30. يعني now the voltage should be in between 0 and 30. At 20 degrees, the volt is 608. So it should be between the value of voltage at alpha equals 0 and alpha equal 30. طبعا at alpha equals 0, the value was 648. So يعني at alpha equal 20, it's less than alpha equal 0. طيب compare it to alpha equal 30. Let's see, alpha equal 30, the voltage was 561. So يعني our solution now is logic. طيب number 3 يا شباب, compute the speed regulation for the firing angle obtained in part B. So you have now part B, you obtain the speed or the firing angle at speed of 1800, but for now you need also to obtain the speed regulation. You know speed regulation, شباب, equals full load speed minus no load speed over full load speed. So for now we need to obtain the no load speed at the firing angle of part B. So simply we can obtain the no load speed like what we have made already in part A, okay, but with the firing angle of part B. So we can say now at part C, we can say now the EMF equals V terminal, which is the voltage at alpha equals 20.1. This is what we have obtained. طبعا شباب يعني here يعني it's 608.4, okay, and there is approximation here, okay, minus 10% of rated current, which is the no load current, because we need to obtain the no load speed multiplied by the armature resistance. So simply you obtain the value of EMF. Now you can substitute in the equation to obtain the no load speed. Once you get the no load speed, you can use the speed regulation relation in order to get the motor speed regulation. Is it clear, شباب? Is there any problem? يعني only what is added here with the solid state converters, we add the operation of the solid state converter along with the motor in order to make speed control for our motor. Okay, شباب? Take care. If the firing angle is constant, this means the voltage will be constant. If you make speed control, you need to change the value of speed. You have to control the firing angle, which means your output voltage will be different. Okay. Another problem here, شباب, the speed of separately excited DC motor is controlled by a chopper. So the circuit now we are going to use the DC chopper one. You remember the relation, the out was equal the duty cycle multiplied by the input DC voltage. So here the DC supply voltage is 120. What's the meaning of DC supply now, يا شباب? Is it the supply of chopper or supply of motor? ها شباب? What do you expect here? The DC supply here, is it considered as the source of the DC chopper or the output of the DC chopper?
The source, I think.
The source of the DC chopper. This is right. This is the constant supply of the DC chopper. What is the output? We don't know. We should control the output in order to achieve a certain speed. So this is now considered as the input supply of the DC chopper. Fine. The value of RA and LA are given. Flux constant is flux or motor constant is given. The motor drives a constant torque load requiring an average current of 20 amps. So this is now the current of the load. Okay. Assume that the motor current is continuous. So we have continuous current, which means it's now you can apply the relation easily without any operation in discontinuous mode, because شباب, we have something called discontinuous mode in DC chopper. However, we are not going to discuss it in details. يعني we discussed recently, if you have the waveforms of the DC chopper, you have voltage during turn on, and during turn off the voltage is 0, and the current we could find the current. So this is V. The current was charging at the turning on period and discharging at the turning off period. As you can see, current is not fall to 0. This is called continuous current. However, if we work in discontinuous mode, we cannot apply the relation of the continuous case. Discontinuous mode means, for instance, current start from here like that and ends at that part and continue as 0. This is called discontinuous mode of DC chopper. We are not going to consider this case in our classes. Just for simplicity. So now we are going to consider continuous case. What is the aim of this problem? Here, it's required to determine the value of range of speed control. So what is the minimum and maximum speed of the motor we can control using this circuit? And range of duty cycle. Okay, this is a typical design problem, يا شباب. يعني after we make the circuit, we need to recognize what is the value of minimum and maximum duty cycle in order to achieve minimum and maximum speed. Okay. For any motor, يا شباب, the minimum speed should be 0, which means that we need to make motor stopping. So in order to stop the motor, we should recognize the value of alpha, or duty cycle. Also, we need to find or define the maximum speed that we can obtain. What is the maximum speed we can obtain, يا شباب, for a DC chopper? You know the relation V out equals alpha multiplied by Vm. You have Vm constant value of 120 volts. So what will be the condition to obtain maximum speed? طبعا maximum speed, يا شباب, means maximum volt. This is for DC motor. So the maximum volt can be obtained here, يا شباب, at which value of alpha? 1. Exactly. So we can now define the minimum and maximum. Minimum value of alpha should be corresponding to 0 speed. And maximum value of alpha is unity, and this shall define the value of maximum speed. So we can say now, starting for the part of speed range. So speed range, we can say 0 speed can be obtained at EMF equals 0. And this can be obtained at Vt equals IARA. And you have the value of current. The average current is given and it's constant. Okay, multiplied by 0.5 ohms. So this is now the amount of voltage if the speed is 0. Take care, here speed is 0. This doesn't mean no load speed. Okay, no load speed means maximum possible speed in the motoring curve at no load current. This is something different. يعني the characteristic what we have is like that. This is for DC motor. This is the no load speed. However, 0 speed means here at that point. So this means the characteristic will be like that. Okay. So for the 0 speed, this is the amount of voltage needed for the A motor. So if we need this amount of volts, simply apply in the relation of V out equals alpha Vn. You will find that 10 volt equals 120, which is the DC supply input volt, multiplied by alpha. So we can say now alpha equals 1/12. So this is now considered as alpha minimum, which will produce 0 motor speed. So what is the maximum speed and maximum alpha? We said that maximum speed can be obtained at maximum possible firing, maximum duty cycle, which is unity. So we can now say at maximum duty cycle, which is 1, we can say EA equals VT minus IARA, and you know that VT is the same as the input voltage, which is 120. For that, the EMF will be 110, and you can substitute in the equation to get the speed of motor at maximum possible voltage. So this now will represent the motor, the maximum value of the motor speed range. So we can say now the motor speed range is from 0 to 2200 RPM, and the firing angle range is from 1/12 to unity. Is it clear يا شباب؟
دكتور,
اتفضل.
if the fire angle or the duty cycle is less than this number, what will be the motor speed?
You will not put any operation for the motor now, because if you have less than this value, substitute with the voltage like that, you will find that EMF is negative. So theoretically, the motor should move in the reverse direction.
Okay, yes.
Which is not our case in motoring mode now. Now we are discussing only motoring mode. Okay?
Okay.
So this is regarding the part of the speed control, and this is a summary for what we have discussed in previous classes regarding speed control. Now let's move to the new part, which is the last slides for the topic of DC motors, which we'll discuss inshallah the following. Starting of DC motor. We already, يا شباب, discussed previously the motor operation at motoring mode. We discussed the dynamic model of the motor. However, now we need to start to discuss the motor starting. Motor starting, it means you have a problem at starting and you need to solve. So we'll discuss this. Discussing the DC shunt motor 4-quadrant operation. And also discussing regenerative braking, dynamic braking, counter current braking, and finally, inshallah, by the end of the topics, we will discuss the course projects. Right. This, inshallah, will be discussed during the next 2 classes. We will start today in the starter of the DC motor, and we will continue, inshallah, next class in that. Let's see first, يا شباب, the problem of starter, of DC motor starting. You know that at starting, or the relation of current equals IA equals VT minus E over RA. Right. At starting, يا شباب, the motor speed is 0. So what will be the value of EMF now?
VT.
EMF will be, if the speed is 0, you know EMF equals K multiplied by omega. So if omega is 0, E will be 0. So
Yes.
E equals K phi multiplied by omega. So if you have 0 speed, so the value of EMF will be 0. This means, يا شباب, that the starting current is VT over RA. So let's see one of the problems before. We had RA equals 0.08 and VT was around 120 volt, like that. And the current was around 20 amps. صح يا شباب? This is in the previous motor problem. صح? Now can you calculate what is the value of starting current in this case? 120 over 0.08. It's a very huge value. I'm not sure the value was 0.08 or not, but if you compare it to a definite motor parameters, it will be very high compared to the rated current. So what we can do?
0.5.
It was 0.5 resistance.
Yes.
And the current, the rated current was 160 or like that. We can see quickly. .05, 20, and the motor voltage was, let's say, at rated here at maximum speed we obtained the motor voltage was 110. Okay, so 110, assume 110 and 0.05 resistance for 20 amps. So if we calculate it like that, شباب, so 110 over 0.05, so the current is 2200. 2200 over 20 amps is 110 times. It's very huge value. Very huge value. So we cannot start the motor in that way. We cannot start our motor in that way because the starting current will be very, very high. So what we can do, شباب, in order to limit the starting current in DC motors, previously the technique was used is to add resistance at starting to increase the value of RA in order to obtain limited starting current. Okay. طبعا you can also reduce the terminal voltage in order to get small current. And actually we prefer this in solid state drives instead of adding resistance. Why? Because adding resistance it's consume some of power during starting. طبعا starting time is not very important because it will not continue for a long time. We can neglect the power consumption at that period. However, even that we prefer instead of adding resistance, we prefer controlling the motor voltage. Right. So the conventional methods were based on adding rheostats, which is called the شباب motor starter. This is the shape of the motor starter. We are not going to discuss it in more detail, just brief discussion because this is became very old. This device is called DC motor starter. Internally, it has many steps of resistances, and when the motor starts working, شباب, there is inside handle. In the beginning, the handle will start at 0.1, which means all of the resistance will be inserted in the circuit. And if the motor speed starts increasing, the value of the handle will be attracted to this core, okay, and it will reduce the resistance value by moving to 0.2, then to 3, 4, and 5 until reaching to point number 5. At point number 5, شباب, it means the external resistance has been removed from the circuit and it will continue working at that point. So this is a device which is called motor starter. Okay. Here we have a problem regarding this motor starter to recognize the operation of this kind of devices. We have here, شباب, a 100 volt motor, 1000 RPM DC machine absorbs 10 kilowatt at rated loading condition and has RA equals 0.1 ohm and is connected to 100 volt DC supply. So the motor is connected to rated. The output rated power the input rated power is 10 kilowatts. The resistance is 0.1 ohm. Now, number A, determine the starting current if no starting resistance is used. Simply you can now divide V over I in order to get V over R in order to get the value of resistance. Starting current. So V over R, yes, but it needs also to be calculated in per unit. In per unit, which means you have to obtain the value of rated current. Rated current can be obtained by dividing rated power over rated voltage. So we can say now IA rated equals 10 kilowatts over 100 volt. So this is now the current rated, 100 ampere. Now, starting current can be calculated as V over R. V is 100 volt, R is 0.1 ohm. So the current is 1000 ampere. So it's 10 per unit, شباب, 10 times rated current. So we recognize now the problem of the starting value. Now, it's needed to determine the value of starting resistance if the starting current is limited to twice of rated current. So we need to make the limit is twice of rated current, and this is safe. For DC motor, شباب, we should limit the current up to twice of rated current. So how we can do that? By adding resistance. So what will be the value of added resistance? Simply, we can say now IA equals 200 ohm, 200 amperes when we add rheostat. So what is the value of rheostat? We simply can write the relation here. We can say now V over the value of 0.1 ohm plus R AC, and this is the value of current. So we can say now, شباب, the resistance is 0.4 ohms. So this is now representing the rheostat needed. The rheostat needed is 0.4 ohms, شباب. This is to limit the current to 2 per unit. Up till now, we got only the maximum value of resistance needed, but for how many steps? This is the question now in order to design our starting or starter device. I will leave part C يا شباب for you to read, okay, in order to understand the operation of starter. And I will give you a hint only. The aim is to keep the current يا شباب during starting limited to the maximum of twice of the load current, and the minimum during starting is rated current. So you should now change the resistance such that keeping the current moving between these two values. So now you need to design steps for your starter in order to make the current moving from maximum to minimum value like that. Yani simply, you need to start at 100 ampere for instant when you add all of resistance. If you remove part of resistance, so at the instant of removing, the current should not increase over 200. This is the idea, شباب. Okay, so I will leave this part for you to read, and if you need any discussion next class, we can continue on this, inshallah. Right. Any question, شباب? Any question? اوكي شباب، يعطيكم العافيه، نشوفكم ان شاء الله الكلاس القادم.